students, we have reached the last lecture in chapter 5. Yay! Okay, so we have to talk about percent yield. And before I talk about percent yield, I need to explain the parts of percent yield. So the percent yield, and we're down here, is equal to the actual yield, which is also called the experimental yield, because it's the amount of product you get when you do your experiment divided by the theoretical yield, that's in theory the max amount you can get. And my cat has come to say hi, so if you hear her saying meow meow, that's her. And we multiply that by 100. So that is the percent yield. Now, again, like I just said, the actual or experimental yield is the amount of product that you actually get when you do the experiment in the lab. And the theoretical yield is the maximum amount of product that's possible to get with your starting materials. That's 100% yield. So if we back up to what we did in the last lecture, what we did was we took a look at excess reactants and limiting reactants, and we said that the limiting reactants are going to limit how much product we can make. So on question 3, we were limited to 230 grams of SO2 right there, and we couldn't make 290. But also 230, that is the theoretical yield. So in theory, this is the most that we can make. Now in number 4, our theoretical yield is 5.13 grams. So in theory, we can make that much. We can totally make less, but 100% yield is going to be 5.13 grams. So the limiting reactant is going to dictate your theoretical yield. Okay, so that brings us to some more problems, and you guys were just dying to see some math again, weren't you? So number 1 says, from the previous question, the theoretical yield of carbon monoxide is 5.13 grams. We just saw that. If you did the experiment and you obtained 4.32 grams, what was your percent yield? Okay, so what we're going to do is we're going to write out the equation for our percent yield again, because the more times we write it out, the better it gets in our brain and the quicker we are with this stuff. So what we have is experimental divided by theoretical times 100. And both of those are yields. So in the experiment, what did you get? So our percent yield, our experimental yield divided by our theoretical yield times 100. And those grams are going to cancel out. So if we do the math on this, 4.32 divided by 5.13 times 100, that is going to give us what? 84.2%. And that's a nice yield. 84.2% is a really good yield, especially for an introductory chemistry student. That's really good. Okay, so number 2 says you react 4.41 moles of carbon monoxide with 8.39 moles of hydrogen gas to get 122 grams of methanol. What is your percent yield? So on this one, what I'm going to do is I'm going to walk you through this entire process, and we're going to put everything that we did together. So I'm going to give myself a little bit more space up here. So what we need to start with is a balanced equation. And you guys have done this before. So we're going to have carbon monoxide reacting with hydrogen gas, and carbon monoxide is CO, and we're going to react that with hydrogen gas. And we have learned that hydrogen gas is H2, so hydrogens don't like to float around on their own. They like to come in pairs. Remember, that's called a diatomic molecule. And this is going to yield methanol. Now, on a quiz or a test, I wouldn't expect you to know what methanol is, so I would probably give that one to you. And methanol is CH4O. You'll also see methanol written as CH3OH, where the hydrogens are split up, and that's a condensed formula, and it's giving us a clue to the structure. And the structure of methanol looks like this if we were to write out the Lewis structure for that. Okay, so back to balancing this equation. We've got 1 carbon on each side. We have 2 hydrogens on the reactant side and 4 on the product side, so we need what coefficient in front of H2? A 2. So now we have 4 hydrogens on each side, and we move on to oxygen. Are our oxygens balanced? Yes. So we don't need to put anything in the coefficient slot for that, but you can put 1s there if you need them. Okay, so now we need to find the limiting reactant and the excess reactant and figure out what our theoretical yield is. So we're going to start with our first reactant. So we've got 4.41 moles of carbon monoxide. Now, in a lot of problems, it'll start you out with the grams. So you will have to do an extra step before this where you convert grams to moles. That's pretty typical. But in this problem, we're starting with moles. So yay, we can go right on to the Multum L ratio. So we have moles of carbon monoxide on the bottom, and we have moles of methanol on the top. Now, you're going to consume 1 carbon monoxide for every 1 methanol that you produced. So that's kind of an easy ratio there, 1 to 1. And then we need to do the molar mass for methanol because we need to have it in grams. So whenever we do the molar mass, we're going to put a 1 next to the mole. And then we're going to have grams on top. And so we would add up the mass for carbon, which is 12.01, and then oxygen, 15.999 or 16, and then 4 times the mass of hydrogens, which is 1.01 or 1.00797, depending on which kind of periodic table you're using. And you guys would come up with 32.04 ish, remembering that that very last significant digit all the way on the right 4, there's a little bit of wiggle room there. Okay, so moles of carbon monoxide cancel, moles of methanol cancel, and when we do the math for this, what we're going to get is 141 grams of methanol. Okay, so we have a possibility of making 141 grams of methanol at this point, but we still need to figure out how much methanol we can make with the amount of hydrogen we have. So let's go ahead and take a look at that. So we have 8.39 moles of hydrogen. And again, if the question gives you grams of hydrogen instead of moles of hydrogen, you'll have to do an extra step right before this to turn grams into moles. But we've started at moles, so we're going to keep going here. All right, so we're going to do Multum L ratio. So we've got moles of H2, and we have moles of methanol up here. And we get these numbers right off the balanced equation. So for every 2 H2s that we use up, we're going to produce 1 CH4O. So the ratio looks like that. And then the last step is exactly the same as the calculation for methanol using carbon monoxide. So we're going to have a molar mass of methanol here. So 1 mole of methanol weighs 32.04 grams. Oh my goodness, my eraser doesn't want to do it. Okay, there we go. Thank you, Mr. Eraser. All right, so 32.04 grams of methanol. Cancel out the moles, and we do the math on this, and what we're going to get is 134 grams of methanol. Okay, so we have enough carbon monoxide to make 141 grams of methanol, but we only have enough hydrogen gas to make 134 grams of methanol. So how much methanol can we possibly make with the amount of reactants we have? 134, that's right. We don't have enough hydrogen gas to make 141 grams of methanol. We only have enough to make 134. This means that hydrogen gas is what? Our limiting reactant or our excess reactant? That's our limiting factor. That's the reactant that is limiting how much product we can make. That means that we have excess carbon monoxide. Okay, so that means that this right here, that is our theoretical yield. In theory, that's the most that we can make. That is our 100%. So if we do the reaction in the lab and we make 122 grams, and we could have possibly made 134 grams, then that means that our percent yield is 122 grams divided by 134 grams times 100. Because 122 was our actual yield. It's what we got in our experiment. So that goes on top. And 134 is, in theory, the most we could have made. And so if we do the math on this, we're going to get 91% yield. And that is really good for a yield, especially in an introductory class. And we are done with Chapter 5. Yay! Okay, see you guys in Chapter 6. Bye-bye.